session. Yeah, the session has been recorded. So this chapter is called conditional processing. So we knowing that in programming language or any programming language that actually permits the that permits decision making or lets you alter the flow of control using the technique called what you call the conditional branching. So in high level language that if statements, your switch statement or conditional loop has the branching logic, and also in assembly language, as primitive as it is, it can also provide all the tools you need for decision making logic. So we will learn about a lot of these things in this chapter. So most of the questions that we actually want to answer, or some basic question, it's amongst them. It's how can you use the Boolean operations in ASM. So we are going to focus on that, and also how do you write the if statement in ASM, and then how nested ifs statement translated by the compiler into machine language. So those are the things that you'll be learning, and again you will learn how to do what. How can you set the individual bits number? How can you perform simple binary data encryption? How are signed numbers differentiated from unsigned numbers? So in this first section of Boolean and comparison instruction, will be actually looking into the following: the CPU status flags, the end instructions, that is the business of the day, and the scope of the test ends up until here. So the CPU status flags, the end instruction, or instruction, XOR instruction, the not instructions, and the application of those instructions. That we have the test instruction and the CMP instruction. So just for a recap, can anyone actually assist us or demonstrate how flags are triggered in assembly language? Anyone? Before we can continue, so that we don't forget, because this is part and parcel of our what we call our test. Yeah. So anyone to assist us? So I will actually write the question again, the question of the test, where we said in the test you must demonstrate how the processor sets the following. Are we all together? Am I audible? Am I audible?
Yes, sir. You're audible.
Yeah, let's just do only these ones. Anyone to assist us? Anyone to assist us here? Who still remember how, or who can demonstrate how the processor can set these things? Who can demonstrate how the processor can set the following: the zero flag, the sign flag, and the carry flag and the overflow? Anyone? Are we on go slow? Hello? Mukalinga? Mukalinga? Hello, guys. Hello? Guys, please talk to me. Mohammed,
Yes, sir.
is there anything wrong, guys? Mohammed, you guys are not talking to me. Are you lost or what's going on? Mama Wolo. Mama Wolo. Okay, it's fine, guys. So to demonstrate the zero flag, you'll actually move into, let's say we are using 32-bit into EAX. Let's assume number 5. Then after that you can subtract 5 from that EAX. So we know that now the result will tell us the zero flag will be equals to 1. And then to demonstrate the sign flag, I'm just taking you through this thing, which is a recap. So to demonstrate the sign flag, you can move into EAX 2 and actually subtract a larger number. The larger number start from 3. So this will trigger the sign flag to be equals to 1. And then another one that you can do is what is the carry flag, right? You can demonstrate by moving into EAX the largest number. You can just say which is the F1, 8 Fs, H. This is the maximum. We know this is the maximum unsigned 32-bit integer, and from it you can add 1 into EAX. Then the carry flag will be 1. And then the last one is the what you call the overflow, right? So you can move EAX or use the Mokosan. You can use the thumb rule. So this is 1, 2, 3, 4. This is the maximum unsigned 32. I mean, this is the largest signed positive number. So you can also add the into EAX 1, and then your result will be negative 214 something. So which will trigger the overflow. So that's how those things are triggered, as we are taking a recap from the previous chapters. So we know even the Boolean instructions like and or except the not, this one can actually also trigger what you call the CPU status flag, right? So we have the AND, which is a Boolean operation which happens between the source and the or source operand and the destination operand. We have the Boolean OR, which happens between the source operand and the destination operand. We have the Boolean exclusive OR, which is operations between a source operand and the destination operand, and the NOT, which is the operation on the destination operand, and then the test, which is the implied Boolean and operation between the source and the instruction, setting the CPU status flags appropriately. So the test, it's like the end, but it only said it during that. It implied Boolean between only the source and the destination operand. So it works like the end. So as we can take the recap, we know that the 0 flag is set when the result of an operations equals to 0, and the carry flag is set when the instruction generates a result that is too large or too small to actually feed into the destination. And also the sign flag, which is set if the destination operand is negative, and it's clear if the destination operand is positive. And then we have the when we say it's clear, it means it's 0. When it's set, it's when it's negative. For example, when we are minusing 2, we say 2 minus 3, it gives us negative 1, which will trigger the sign flag. And also if you say 2 plus 2, obviously, or if you can say 5 minus 3, the destination operand is positive, so it is clear, which is going to be 0. And then the overflow flag is set when the instructions generate an invalid signed bit. And then so bit 7 carries is XORed with the bit 6. So that is one of the examples that you can use. You'll see them in the examples that we'll be having today. We have the parity flag, which is set when the instruction generates an even number or of 1 bit in the low byte of the destination operand. The auxiliary, which is set when the operation produces the carry out from the bit from bit 3 to bit 4. So we have what you call the end instruction. The end instruction, this one, we call them bitwise, or all these things you call them bitwise. What? You call them bitwise what? Hello? Hello. Hello. Are we okay, guys? Or I'm just gonna be here to talk alone. Come on.
Yeah, hello, sir. Yeah, repeat the question.
I'm saying we have the end instruction. What we call them bitwise, right? Or can or it's this thing you can call it which this thing you can say it performs a boolean. A boolean you can either call it bitwise or boolean, right? Right. Hey, Mkhala,
Yes,
are we
you're right, sir.
yes, it
What is
performs
it?
a
Bitwise? What?
bitwise boolean or bitwise. You can say it performs a boolean or bitwise AND operation between each pair, matching its each bit into operand and places the result in the destination operand. For example, you can recall from chapter 1, if we have a truth table like this, if you have a truth table like this, whereby you have x, y, where x will be 1, 1, 0, 0, and y it's what? Y it's what? 1, 0, 1, 0, isn't it so? Hello?
Yes.
And then we say what and what?
One
We say x
Then
and
X
and y. So obviously if you say 1 and 1, that will return what? 1.
one.
All will be 0. So this is only set if what? If what? So
If we
for
have 1 and 1.
no, we can say for each, right? If both the bits are equals to 1, then it means what? The result is it's 1. Otherwise,
It's 0.
it's 0. So that's how the AND works, isn't it so? So the syntax for AND, it's you can say AND. So you have the destination operand, the destination. Okay, let me do this. You can the syntax for it, you can say AND. This is the destination, and this is the source. And we have how many variant from it? How many variant do we have from it? Or how can this or how is it permitted? Hmm?
Our destination can be a register and source,
I
and
can't hear you.
okay, we can write its combinations are end, register,
Yes, it can be from firstly
register.
from the register and the register, isn't it
Yeah,
so?
yes, and then register and memory,
Okay.
memory into register.
It
Yeah,
can be register to register, and again can be memory immediate value. It can
okay, yeah,
also be what? The memory and the register.
yes,
It can also be what? Register and immediate value, isn't it so?
yes, also
And then it
register
can also
and
be
memory.
register and memory. isn't it? So we have how many variant? 1, 2, 3, 4, 5, if I'm not mistaken. So those are the only permitted combinations for that operand, isn't it? So hello.
Yes.
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 So yes. So you can even see from here when you say and, if you have in 8-bit number 001111 1110111, and also 1111011 and 00001111. If you end both of those binary numbers, you'll have the first one will be 1, because the rule says if both bits are equals to 1, then it means the result should be 1, otherwise 0. Even the second one should be what? 1. This one should be 0 because only one bit it's 1. This one should be 1. Oh, this should be 0. This should be 1 because both of them are 1, and then the rest going forward will be zeros, right?
Yes.
Yes. So yeah. So we have again this guy called what? The OR instruction, right? So the OR instruction, this one performs a Boolean or performs a Boolean OR operation between each pair of matching bits into operands and place the result in the let's insert the blank page. I don't know if doing this it's actually wrong. If you can follow from whatever that can you follow from what I'm writing here? Hello.
Yes.
Nothing wrong, ne? Hello.
Ah, there's nothing wrong.
Okay. Now this we know the syntax for it. It's what you can say or, and then it will have the destination and the source. This is how or works, isn't it? So the or uses the same operand as what and does. So it has the following are permitted in this. So you can or something from the register to what? From the register to what?
Register.
From memory to what? This is memory to register. Remember, this is the destination.
Yeah, the other.
I don't know if you get it.
Yes, sir. Then
Immediate value into the
register.
register, isn't it so?
Yes.
And then register into the memory, right? And
yes.
the immediate value into
the memory.
Into the memory, isn't it so? So given the truth table, if you still remember the truth tables, you can recall that with truth tables. Let's say, for example, you are given X and Y, right? And you want to OR them. And then we have 1, 1, 0, 0, and 1, 0, 1, 0, isn't it so? And then we'll still have to demonstrate this thing on MASM. So let's make sure that we finish early. So we know that if the operation this works like this, or instruction is useful when you need to set the actual number into 1, right? So what happens with or? The difference between this one is that at least 1, right, bit should be 1 in the combination, isn't it so? Hello.
Yes.
Otherwise, it should be 0. That is how the OR works. Mr. Mkalinga. So we know that 1 and 1 is 1.
Sir,
1 or, hey, Mr. Mkalinga.
you see, when we were doing the operations,
Mm.
that part is fine. But when you say memory to register, memory to immediate view, why are we saying that? Where is that coming from? What's happening there?
So, for example, you can't come and say, for example, we say we said the syntax of this is you can or from what? From this should be the destination and the source. So those things are either the register. The registers consist of what? Consist of what?
Well, ECX, EAX, those registers.
EAX, ECX, those things. If you still remember the EAX, EBX, ECX, right? So immediate values are things like 10H, you see, and then you have your memories, the 1040 something, isn't it so?
Oh, so that part wherein you have the source and the destination, we are trying to represent the X or Y in it's not to represent X or Y in assembly language.
No, you will see because I think you're confused now. This is how the OR instruction or the syntax of the OR instruction in assembly language is. So you must have
Okay.
the destination and the source. And the variant are as follows. You can only OR the register into a register or the memory register and immediate value register, the register memory and the immediate value memory.
Okay, so
So that is
makes a
the
bit of
only
sense.
permitted, these are the only permitted way to OR your operands in assembly language.
Okay,
I don't
thank
know
you, sir.
if, yeah. So if we say OR, we know that the truth table will end up like this, right? So on the end, I forgot something, isn't it so? So if you or something, so the flags that are actually where was end? This is end, right? So the flags in the end instruction, it it always clears the flow. When something we say is clear, it means it's zero, right? So the overflow and the carry flag, and it will modify the following flags, which is the sign, flag, the zero flag, the parity, and the parity flag. So with the OR instruction that we are doing now, the flags that are actually going to be triggered, we know that the carry flag here with the OR, it's always the carry flag, and the overflow always clears or cleared, but modifies the what, which flags, the ZF, the SF, and the again is the what, is the PF. So yeah, are we fine? Are we fine?
Yes.
So we have again what you call the XOR, right? Moshad, Kegan, AK, K. Okay, let's move forward. You'll reserve your question for later. Okay. So we have again what we call Mr. Exclusive OR instruction. This guy performs a Boolean exclusive OR operation between each pair of matching bits into operands. So you can see if we have the what do you call if we have the truth table like this for exclusive OR, the syntax for XOR will your XOR destination, and then you'll have your source here, right? So the exclusive OR truth table is like this from your SCSC 0. It's SCSC 0 what? 011 SCSP 000 and so on and so on. So this is how it looks like. So you'll have your 1 1 0 0 and 1 0 1 0, and then when you're using exclusive OR, you know when the bits are the same. If you have 0 and 0, then it's 0, and if you have 0, if you have true and true, it's 0. But if you have bits that are different, then you can say it's 1 1. So that's how exclusive OR works. So it said with bits that if both bits are 0 or both bits are 1, the result should be 0. Otherwise, the result is it's 1. So the flags or the status flags that will be triggered, right? Okay, let's start with the status flags that are always clear, right? So it clears these ones, the overflow and the carry flag, and modifies the SF, the ZF, and the PF. So yeah, that is all with the XOR instruction. So again, you have the NOT. You know the NOT is simple. If you have true or the NOT instruction, actually it's used to color invert all bits in an operand. The result is called one's complement. We know that anyone who still remember what two's complement is and the difference between this one, the ones and the hello.
Okay, the not operator is like the one's complement. To differentiate it from the two's complement, with the two's complement, we have the one's complement. After that, we add one. The difference is that the other one is not added with the other one.
Yes. So yeah. So that's how the NOT is. So if you have the following, let's say for example, the following binary,
Sir.
1 0 1 1 0 1 0 0 5 6. Yeah. And you say it, and this is X. If you say not X, Mr. Mohammed, I'm listening very carefully.
Okay. I see you are doing not. I just wanted to ask what you're doing because my connection was bad.
What are we?
What y'all were doing because I went out for a moment.
Oh, we are done with X, or I don't know if if anyone understand, command, are we all together? Mkalinga.
Yes,
Sir,
Mohammed, we are
sir,
doing the not instruction.
Okay, thank you.
Mkalinga.
yes, sir. I don't know if I'm getting those concepts, but if I get you right, you're saying as we use those operations, the and, the or, they clear certain flags and set certain flags.
Yes. So yeah, that's what I'm actually explaining here. So we'll actually
All
do
right.
that in coding. After that we have to do a code, isn't it? So to demonstrate that.
Okay.
You are not going to rely on the slides because this code on the slide might actually uh, mislead you. So if you have this, now we are on odd, Mr. Mohammed. So the not, we know that if we say not x here, it will be 0 1 0 0 1 0 1 1. That is not x. And the so the operand types that are permitted are, or you can only not the register and not the memory. These are the only, or these are the variants for the not. So with the not, note this. Even if the question comes, do not make that mistake. No, hear me here. No flex are what? Are set or affected or triggered. Are we all together? Hello?
Yes. Yes.
Are we all together on that one?
Mm.
We're not going to make any mistake.
No.
We're not going to make any mistake, like before when I said the move instruction does not trigger any flag, and the nag. Do you still remember when we say, was it the nag or the what, which does not trigger a certain flag? What was it? Mukalinga?
You
Mukaling?
won't make a mistake.
Eh? You want to make a mistake, Mukalinga?
I
No.
won't repeat it.
Have you ever made a mistake?
Yeah, I did. I won't repeat it.
So now there are some applications which actually manipulates the the set of items selected from the limited sized of universal set. So let's take, for example, you have the following set. So let's stay away from the slides a little bit, because this one, when we talk about a bit mapped set. So with bit mapped sets, this is what happens. Suppose that you have two sets, right? Which is set what and what? Set A and B, isn't it so? So suppose that you have the following set, right? Okay. For instance, we can say we have a bit which consists of numbers 7, 6, 5, 4, and 3, 2, 1, and 0, right? So, and you have set A, which is equals to, let's say, binary 1, 0, 1, 0, 0, 1, okay, let's just say 0 1, right? And set B, which is equals to 0 1 0, and then 0, and then what? let's say 1 1 and okay, let's say 0 0. So we have two sets here. So the bit set. So when you are saying bit set, we are talking about the bit patterns or the sets where the bit is only 1, isn't it so? So set A. So from this set A, we know that the sets from set A sets are what? Are from bit number. Let's go. Are from bit number. Hello.
Is it set?
It will be 0. This is bit number. It will be 0, 2, 5, and 7. And set B will have 2, 4, and 6, if I'm not mistaken. 0, 1, 2. Not 1, 2. It can't be 4, isn't it so? It can't be 2, 4, 6. Is it 2, 4, 6? But I made a huge mistake. It's 2. It's
2 3 6
2, 3,
6.
6. So those are the bit set. So if you come and say maybe you want to apply the union, we know the union is what in ASM. The union is what? Union is what? Hello.
2.
What is
All
the
the
union?
elements of set B.
Is 2. It means you're going to be using the OR instruction, isn't it so? The intersection is what? It's what is the end, isn't it so? And again we have the what? The difference, which is the what? Huh? So the difference is where you can use not from AL or what not. Oh, let's say for example we are having a set of instruction where we can say move AL set A, having that, and you can actually not BL, and then you end AL BL. So yeah, so that's what we call the bit mapped sets. So you can see them from here, where when you are set complement start, the intersection is where you're using the end, and the union is where you are using the OR. So I will actually pause from here. I don't want to do this application from the slides. We want to do our own code, isn't it so, guys? Are we happy with that?
Yes.
Are we happy
Yeah.
with doing our own code? So we can actually have our code. So wherein in our code we will demonstrate the following. Demonstrate the end instruction, the what? the or, the exclusive or, again what, the not, and the test. So we didn't talk about the test, and also let's continue and talk about the CNP. Yeah, let's finish up with the rest. So we'll come back to this one. So this one you'll read them alone. So isn't it so, Mr. Goma? Because I don't usually set from the slides. I set from what I actually teach, isn't it so? So the test instruction performs an amplified and operation between each pair, right? So what happens with this one? It performs the amplified, or it's a this one performs a destructive and operation between each pair of matching bits into operands, and this actually sets the following flags. So the flags that will be set if you end something and something will be the following. Let's do this. What's going on now? We have now. So the test instruction. We said it performs an amplified and operation between each pair of machine bits into operands, and said the following. It says the following. It sets the sign flag, the zero flag, and the parity flag. So, but this does not only said it or just said it like that. It said it based on you must get this based on, it said it based on the values. Don't make any mistake. Assigned to the destination. Don't make any mistake with the test. So it sets this sign flag based on only the values that are assigned to the destination. So the difference between these two, the test and the end, is that the test does not modify the destination operand. So the test instruction permits the same operand combination as the end. So do you still remember them? The permitted set of statement in the test. Hello? Hello?
Yes,
Do you
I
still
agree.
remember?
The test it's an amplified and operator. So uses set is
Sets.
yes,
Okay. Are we all together? Do you understand though? So, but it's fine, Oaks. So we know from end, if you still remember or if you still recall very well. So the end instruction, it has the following operands combination: the register, memory, immediate value, this. This is what I was talking about. You can move this thing into the destination. Could be from register to register, from register to memory, from immediate value to memory, from immediate value to register, from memory to to register. So that's why we say the test also has the very same combination as the SDN. And it says which we said it says which flag, SF, ZF, and the PF, provided it's given the value that actually triggers all those things. It is based on the values that are not that always it's going to trigger the instructions. And then we have the last one, our last guy, which is the CMP. So this one, the CMP, you can call it the compare instruction. So this one performs an amplified subtraction of a source operand from a destination. So neither the operand is modified. So what happens is that the destination, okay, the test, if I forgot. So the test instruction will have the following syntax. You can say test, and then you have this is the destination and source. And also this still applies with this guy, CMP, the compare instruction. So the CMP, right, syntax is also CMP, compare destination and source. But what happens is that this is an amplified subtraction. What happens is that it subtract, but neither operation is modified, so it doesn't change anything, any value that is in the destination or either the source. So what happens is that the following flags will be changed. So it sets the what? The overflow, the sign, the zero, the carry, auxiliary, and the parity flag. So that's are the flags. So this one is based on the value of the destination operand. So that's what how the CMP works. So now we can be confident. Any question that we can do a code? I don't know. What should our code do, Misters?
Say, I have a question.
Yes, Tata. So let's do this. So let's write maybe a code that can. Hello.
I have a request, Nyana, if this is possible. Ne? You see, this code, this is what we were doing last week, right?
It's Mukalinga.
The global labels, we say.
The what?
The global labels. Can you hear me say?
The global labels, yes.
And all that
And the
stuff,
local one.
passing parameters in assembly language to all those things, you know. At the end of the class, can if it's possible, can give us a scenario wherein it does include all those things so that we can try and work on it, Nyana. Have an idea of
Okay.
what's really
So you
happening,
can okay.
that one
Your
will be
question
for
is
us.
that I should show you a demonstration of how the parameters are working.
Not it's not a question, it's a request for you to give us maybe a scenario to code that
Okay,
will
I
help
will
us
give you a scenario to
understand all
code of
those
global labels. So, but let's do it because we no longer have time. but I will actually demonstrate the local labels. And also, if we still have time, I'll also demonstrate. If I'm not gonna finish with it, I'll actually remind you on Friday so that I can demonstrate the what.
The labels.
So yeah.
No, it's fine.
Yeah, so but let's do this. This one, let's demonstrate the, what do you call this? The Boolean Boolean and comparison instruction, isn't it? So we can just name it what can we name it? The Boolean and comparison. And then after that, we need to put this thing and we name it BACI.ASM. And then let's see the BAC. So we can come and copy, as always, the template from here until remove everything in here and also clear the data in here. So in this thing, we will actually demonstrate what. Okay, let's do this. Before I even did it too, let me just write actually a comment. Yeah, let me just say here we will actually I'm not so sure if you guys can see from your side, né? We demo the and can you see? Hello?
Yes, if a person can just
If a person can what?
can zoom.
Can I zoom?
We can zoom from our side.
Okay, let me do this so that you don't mess up with my let me do this. So you can zoom from your side. So in the data section, let's initialize two values, right? The values should be this. Let's just say we are going to initialize the values 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And last one should be 1, 2, 3, 4, 5, 6, 7, 8. Am I in the right? No, I'm in the wrong. This is not cool. Okay. You will actually eliminate the 4 zeros and the 4 ones in each and every, because this is too long. Yeah. So it will be 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then last one, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So we know the first one is 0, the second one is F, and then the other one is 0, and then the another one is F0, F0, F. So we initialize our first value to be 0F, 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 and we can initialize our another value to be 0, 0. Let's just say 0, 0, FF. And let's just initialize it like this: 0, 0, FF, 0, 0, FF. So our variable one, or we can call it x1, you name it. Let's just say var1 of d weight, and then you say 0 f 0 f 0 f 0 f 0 f. I don't know. Are they 8? Are they 8? Hello? Let's be together here, guys. Hello? Or should I stop? Hello?
9, sir.
And
Yeah, so
10.
if you stop, will we pause? Say?
Because you are not answering me, and then I expect you guys as to actually. No, you will pass. Given I'm given the impression that you guys maybe understand. Because I hope that when me making this mistake,
says Morin.
so let's have the message for end, right? And call it the MSG. Let's just say end, right? And you know this
Sir,
course
wait.
has been doing.
Wait, sir.
Yeah.
You see, variable 1, it has 7 hexadecimals. Because usually we don't count the first 0 because it's just differentiated from the rest that it is not a string.
So, but did you know that? But did you know this thing? It fills it from the least significant bit, which is the right. So obviously the last one will be 0, isn't it so? If
Yeah,
you
I
are
see
going
it.
to know, eh? Do you understand, my friend? Are we together?
If you start with F, it will take it.
Eh? Oman,
It's fine like that.
I can't
I
hear
have
you.
network issues. Sir, I have network issues.
Okay, it's fine. So let's do this, and then let's copy this thing. How many instructions do we have? We can have. We say the or, and then we have the or. We have the XOR. We have the what? The not, the test. What is the other one? The CMP. Okay, let's do what I mean CMP. Okay, let's just demonstrate 2 CMPs where it shows 2 equal numbers and the other one which shows 2 unequal numbers. Yeah, so we can have this one.
Sir,
So in here, hello.
I think I don't understand why did you initialize var1 to those values? Why use those specific values?
You can use the values that you want to use, but this thing is the same as that thing of true, false, true, false, true, false. If you can see it.
No, I don't see it. Yes. Mhm.
Or you can initialize it to f what do you call f what f0 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 f0, or you can initialize it to f0 and f0 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 f0. I don't know if you get
So the F kinds of represent that one.
f represent what?
Represent that one, the one we had.
The which one, Mr.
No,
Mkalim?
it's not one.
What is it? Assist me, Gush.
Isn't F represents
4 ones.
yeah, it is the last
Oh,
value. Like yeah.
right. Let's go. Yeah.
Zikobuya Mkalinga.
Too much. Sir.
No problem, Mkalinga. Then this thing you can just say it's or here. X or. I'm going to have a serious problem. This thing of initializing these things. Not test CMP1. Then this one is CMP. And this one, let's say it's new line byte, and then we say it's 0D H 0 AH 0. And then in the code section, we start with the end. So this is how we're going to demonstrate our end. So in the code section, this one should come here because the one that ends the main. Yeah. So in the code section, let's start with the end. We can just do it like this. Too much decoration. Mukalinga, are we fine, my friend?
Sir. Sir.
Let's start with the end. Did I make any mistake, Makalinga? So the end for first one, let's move val1 into. If I may, this val1 does not belong here. Oh, it belongs here. Let's move val1. This is not it. EAX. Why are you guys not telling me that I'm making mistakes? Guji, and again, let's move EBX var2, and then thereafter we do what? We move the offset of that message into EDX. We move the offset of message for end, MSG end. And then what do we do after we call write? We write what? What do we write?
Write string.
We write the string, call write string, and then from there we can call the next line C RLF, ne? And then from there.
So on top there in .data, why did we initialize new line?
New line.
Yeah.
This one we are going to put it at the end.
Okay.
Yes, Mr. Which Mr. are you? Hey, Mr. Mukalinga. Are you Mr. Mukalinga? Mr. Mukalinga? Oh, it's Gucci.
It was
can
Guji,
call.
sir. It's not me.
Oh, let's call them registers. This is how the end is. You see, we moved the variable 1 to EAX, variable 2 to EBX, and therefore we moved the sort of message end into that and call write string. From there we use
The spelling of regs.
So you made a mistake.
Yeah, I made it. I wanted to see if you guys are with me. So yeah, at least we are together, ne? So this one it will be for all. Let's be fast. So the logic is still the same, isn't it? So here the logic is still the same, I guess. So the logic, if it's the same, will come and copy from here, copy and paste here, and then change this thing to what? To O, and change here to what? To O, isn't it so? Mukalinga. Paste this one and
It's,
change
it's
it
like
to X.
it's like
Eh?
it's like that. It's like that.
Why are you saying it's like that, Madam Kalinga?
No, you're very
And here,
right.
yes.
You're very right.
What if I'm wrong?
You can never be wrong.
That's you. That's not me. Now I'm not a perfect human being. So I assume that not everything that I do will be up to perfect. So where I made mistakes, you guys must come in the codes and actually let me know, isn't it so?
Yeah.
So this will be the knot. So the knot will be different from them. So it means the knot we can move. What can we move from knot? Let's just move. Let's not be fancy and move variable one and check this guy out. And say message here will be not, isn't it so? And then call write string. And we not what? EAX. Is it fine? Is it fine? Hello.
Yes.
Then this one should be the test. And then we move variable on the offset of message test. Call write string, call CRLF, and then we test EAX. Test EAX, EBX, isn't it so? And after that you call the dumb registers, and then oh my god, and then the last one is the CMP, isn't it so? So the CMP, in the CMP, let's move different values. Let's just say we move 5. The first CMP, let's call it CMP what? 1. CMP 1. And then we move 5 into this, and then again we can move 5 again, the same value into this, and we call the message for CMP1. And then we call write string, call CRLF, and then from there we can have here and say we want to what? To CMP to compare. We said the CMP does what? It's an amplified what? We said it's an amplified what?
So if we take it as this way, it just compares two registers or
So
something.
we said Guji, we said it's an amplified what?
I don't remember exactly, sir.
Guji. So here let's
It's
say
an amplified subtraction.
it's an amplified subtraction. CMP2 call write string, we call CRLF, and then we CMP EAX and EBX, and after that we call the dumb register, we exit the program cleanly, and then so you get it, or you want to forget about it? So should we run it? Should we run it? Should we run it, guys?
Yeah.
Yeah, let's run it and see. Let's run it and see.
And see the errors, ne?
I don't know if there are any errors.
Kalinka, okay, let's save the program.
There's no
Save.
errors.
How sure are you? Then let's put this thing here and try to run it.
100%.
And let's do this. Yeah, it has assembled, nothing was deleted, and you can press enter. Then which guy are we going to start with? Can we? Is it possible? Yeah. So let's start up there. So we're going to start with the first one, the end instruction, right? Isn't it so, Mr. Mukali?
Yeah, it is so. Sir.
Is it like this? Huh?
The end instruction.
Yeah, is it like this? Do you still remember what was happening?
Yes. Yes.
What was happening? What was happening? Remember, we have initialized our variable one to be. Let me just do this.
Yeah, so
So that
our EAX
is it fine?
No, it's not the same as the way we initialized.
We remember we have initialized our value to what? 0f. I get.
Yeah, 0f,
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 0f.
1, 2, 3, 4, 5, 6, 7, 8. I get.
Yeah.
And then again we have initialized to 0, 0, f, f, 0, 0, f. Now they say our EAX is 000 f 000 f, isn't it so? Now EAX for the first one is 000 f and 000 f, isn't it so? And then we said the end works like what? So with end, if two values are 1, it means what? Is that value, isn't it so?
Oh, so it changed the. It
So
stored
the rest,
in the
these ones
EAX.
that are what will be false. Isn't it so?
Yes.
Yes.
Yes. I
Yes.
get it now.
So remember that this F here, you still see this F here, right? Or let's start with the first one. They are represented by 1, 1, 1, 1, 1, 1, 1, 1. 1 and 1, 1. 1 and 1, 1. 1 and 1, 1. 1 and 1, 1. And this is what? F. And then you have 0, 0, 0, 0, 0, and 1, 1, 1, 1. This is what? 0, 0, 0.
0, 0.
Isn't it so?
Yes.
Huh?
Yes.
So if this guy is like this, it means this guy will also be like this, and this guy will also be like this. But this guy will be the same as this guy, and this guy will also be like that. So do you understand why our EAX is equals to 0, 0, 0, F, 0, 0, 0, F?
Yes, sir.
And then we said which flags are triggered. We said which flags are triggered. We have the can flag, which is set to 0. We have the sun flag, which is set to 0. We have the what? Huh? So this one does not show.
Zero flag.
Zero flag, which is set to.
Huh? Ukovaravar. So we move. So you can see from also the XOR, right? This apply on the OR. So initially we had 0F, 0F, 0 what? F, 0F, 1, 2, 3, 4, 5, 6, 7, Is it like this? Is it like this?
Yes.
So if we OR both of these things, we expect to find what? F, this one, F or F. It should be
F.
okay. 1 or y. What is 1
It's F, sir.
or 1?
Yeah.
Is it 1?
Yes.
So, yes, this should be F. And then this should be
F.
and this should be
F.
and this should be 0, isn't it
0.
so?
Yes.
This is what?
F. F. F and 0.
So is it like that?
Yes.
I can't see it. Oh yeah, it's there. It's like that. So you can see it, and then you can check the XOR, and then let's move to NOT. You see, so we just said not we noted the what, the 0 1 2 0F 0F 0F. So note of this, it will actually be 0. This will be F. This will be 0. This will be F. This will be 0. F 0 F. Hence will be F 4 4 4 4 4 4 4 here. 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 So the X or the exclusive OR. We know that exclusive OR with exclusive OR. How is the exclusive OR?
When they are the same, we get 0.
When they are the same, we get 0, either 0 or 1.
Yes.
So it means we are having 0F 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 0F. Hey, I did many things, isn't it so?
1, 2, 3, 4. So
Where's the
wrap the last 2. Last 0F. Yeah.
So it's fine now.
Yes.
And then we will have what? 0 0.
0.
What did I do? Okay, it's fine now, ne?
Yes.
So you can see, but I'm having problems, Mr. Guji. So it's going to be 0 0 F F 0 0 and F and F. So if both are the same, it means what? It's 0, isn't it so?
We get 0.
Yes.
So this is going to be 0. This is going to
Wow.
be F. It's
F.
going to be F. It's going to be 0. It's going to be 0 F F 0.
0.
Is it like that?
Yes.
Yes.
Yeah. So the note we did it, and then we have the test. Hey, what's going on? So we said the test is only it's an amplified what, so it doesn't change. So it's an amplified, not the amplified end, right? So it doesn't make any effects on the register. So you can see that the 0F0F is still the same. The 00FF00FF is still the same. And then the last one we have the CMP one, this guy. So we moved
Sir,
5 in
I
EAX.
never get what test instruction does.
We never got.
I don't understand. It just takes, like,
It
what does
takes
it do?
what? So the test instruction, what happens with it, is that It performs. We say it's an amplified and operation between each pair of matching bits into operand, and sets the following flex. I got sign zero parity flex based on the value assigned to the destination operand. So the value that is assigned to the destination operand did not trigger the flex, but at the end of the day, you see, this thing, it's an amplifier. It does not actually change the values that are in the destination, or the destination is not affected once you say test. But if you test something and actually you have the value that actually triggers this, you'll see it. If these values were able to trigger sign flag and zero flag, and you will see you were able to, or you're gonna be able to see which or which flags were triggered, and that the test is working. Unfortunately, now it won't show
So,
anything because this values does not trigger any of the following flags.
so it checks the registers, and then if they are fine, then example, if we had EAX as what to call as zero, so then the zero flag was gonna go.
So what happened is that what
It just
I will do, ne? What I will do, ne?
yes,
I'm gonna give you, this is your homework. You're going to have a homework because now we think we are left with few minutes. Your
yes, sir.
homework is to go and test what this guy does, isn't it so?
Okay, sir.
Not test. Oh, what you are going to do is to use the test instruction, right, to trigger the CF. We said it triggers the CF and the what? To trigger the CF, the zero flag, and the parity flag. These three flags that it triggers, right?
Yes.
I'm gonna put it as a quiz now. Once you're done, it's going to close 5. So
Okay.
we have the CMP where we moved 5 and 5. You can see the CMP also, we said it's an amplified subdirection, right? So the amplified subdirection does not change anything in the destination or either in the source, isn't it so? So what it will do, it will do those subdirection. Hence, after we did that, we said 5, 5. So the amplified subdirection is going to minus EAX by EBX. Then it will trigger which flag? Which flag was triggered there? Yeah.
Zero flag.
You guys are not serious. And then the last one, it's this guy, the CMP2, where we moved 3 into EAX and 7 into EBX, right? And then we know 3 minus 7, it's negative number. So what we get? We get that we have moved from an unsigned value to a signed value. So it means the value that is going to come after that is going to be negative something. That is why we are going to experience the carry flag being triggered and the sign flag being triggered. So yeah, are these things difficult?
No, sir. You must bring them in the test.
They are not coming.
Ah,
So I guess we demonstrated these things. Therefore, on Friday we'll do the conditional jumps, but the test will end up until slide 20. Slide 20.
thank you,
But
sir.
this thing,
Thank you.
this one, eh?
Thank you, sir. Until slide
Until you
20,
reach
which
until
is
here.
yeah, which is whatever we did today, isn't?
Yeah. So
Okay.
don't make any mistakes. So how was today's class? How was today's class to get
These things are
feedback from?
coming in the test.
No.